Well, hello everyone. Welcome to the final presentation of our Capstone project, Intelligent Traffic Monitoring. My name is Grishma, and today, along with my team members, Ricky, Uni, Akir, Anusha, Amanda, Anandita, and Aaron, we're going to be showing you what we did this semester. Our Capstone mentors are Dr. Alessandro Aldramari, Dr. Kashima, and Dr. Jonathan Francis, and they're actually here with us today, so thank you for coming. To introduce our project, the rising domain of intelligent traffic monitoring plays an essential role in improving road safety and security of smart transportation systems. The main aim here is to detect vehicles, pedestrians, and possible intersections of the two, both normal and anomalous. We also want to look at any other relevant object in the scene and track their trajectory so that this combined information can aid the decision-making capabilities of driving systems with respect to real-time traffic situations. So, in summary, ITM, or Intelligent Traffic Monitoring, can be stated as the problem of deriving actionable knowledge from multimodal information, real-time and background, available to us due to the abundance of traffic data points and usable image, video, and text data. The goal is to build smarter and safer systems for intelligent traffic monitoring. Okay, so coming to our problem description, the problem at hand is to extend a neural network-based learning method, HANS, to understand traffic scenarios. The current method is limited to regulatory traffic monitoring, leaving scope for improvements with respect to anomaly detection. HANS was developed by Bosch, and we were working on trying to extend it, basically. In order to do this, we suggest an ontology-based approach, which builds a knowledge graph from curated data sets. This would be further fed as input to our vision language model, which would not only give us the classification results, but also a reason for such a classification. Why is it classified this way? This monitoring system, when deployed, can be used to enable human operators to dispatch relevant services, such as parking enforcement agents, police patrols, ambulances, etc. Coming to the major features of our system, there are three major features that we have identified. The first one is multimodal traffic data input. This consists of cameras set up at intersections and also potentially the dash cams in cars. In terms of vision and text data, we will be using a multimodal dataset DOTA, which we will go over later in further detail. The second part of our component of our pipeline is the knowledge graph. It's basically a high-level reasoning on traffic anomalies, and it's based on symbolic and latent knowledge representation, where we identify the objects in the scene and capture the relationships between them. The final part is the anomaly detection classification model. We basically train a machine learning model to detect an anomaly from a fixed set of classes. And as a stretch goal, we aim to provide localization of the accident in the frame and also a generic text description that describes the actual accident. Moving on to system functionality, let's first take a look at the requirements of the system. We are required to build a system that detects and classifies anomalies from surveillance traffic data. It should also produce other metadata, such as a description about the accident. The people using it should have varied access based on their role. For example, traffic operators can just get the information on the type of anomaly identified and the metadata. But for Bosch clients, we would also have access to the ontology definition itself and our vision language model in case they want to modify it. Coming to our non-functional requirements, we have many. The first one would be performance, and in this mainly we are looking at high recall. What this means is that, for example, if there's a major road accident and the nearest camera connected to the system does not have a good view of the accident itself, it should still be able to classify it as an anomaly and alert system administrators. So what this means is that if the system is not confident, it should still try to minimize its false negatives. So that's optimizing recall. The second non-functional requirement is fairness. So the performance metrics, that's accuracy, recall, etc., should be equal across all categories of anomalies. So suppose there's like a rare accident that occurs, such as a car going the wrong way, the system should be able to detect the occurrence just as well as common incidents, such as a car going normally. There's also transparency, which is we need interpretable and transparent results through the knowledge graph. So a traffic operator, if they notice several inconsistencies with what they have seen and what the model is predicting, then they should be able to understand why the model is making such a prediction and how the system's arriving at this conclusion. Finally, we have security, reliability, which is like 99% plus uptime, traceability, like bug tracing, usability, maintainability, and modifiability, where, if something breaks, if we want to add new cameras, we should have leeway to do all of this.
Yeah, as for the resource requirements of our project, so we actually explored different data sets such as traffic QA, data, and DOTA. And then we finalized it to be DOTA because it has the most abundant annotations, tracked objects, and labels. And then as for the computation, we are currently using Google Colab in connection with GCP VM instances. And then this is the design overview of our system architecture. So basically we have four major components. First, the Google Drive where we store all the data, or the data loader we define, or the verbalizations. And then we'll have the multi-model model, which will give us the multi-class classification results. And then we'll go more into this later. And then for the traffic understanding component, it is a module where we define and populate a knowledge graph based on the ontology that we together defined. And then this is also queryable using Sparkle so that we can get verbalizations and informations from the knowledge graph. And then finally, it is a hypothetical module. It is the monitoring system. So hypothetically, a traffic operator should be able to look at the system and monitor the anomaly in real time, but this is not within scope for our current project. And then as for the implementation overview, this is just another look at how data flows within the system. So basically during training time, we'll input the data into the knowledge graph, populate the knowledge graph and get information from it. And then we'll feed that into the model together with the frames, the videos and images that we have from the original video. And then from that, the model will give us multi-class classification results. And then at inference time, we'll skip the knowledge graph part and then basically directly pass in the videos into the model. And then that will give us multi-class classification results.
So this is the milestone plan that we have been adhering to this semester, and we were able to seamlessly work through our plan along the way. And let us just dive into more detail of our project. So in terms of the data set, we decided to use DOTA data set that contains over 4.5K traffic videos obtained from YouTube. Interesting thing about DOTA is that it classifies the video into either egocentric or other class, which those further subdivided into 10 anomaly categories, resulting in effectively 20 different classes. So screenshot on the right here displays the metadata of the DOTA dataset. Basically, DOTA is built around three primary questions about when and where the accident happened and what accident it was. Videos were sampled based on 20 frames per second, and we used the anomaly frames based on the annotation provided in the metadata to proceed with. So these are the examples from the actual DOTA dataset. So left one displaying the example of egocentric accident video, and one on the right falls under the other video as the dash cam itself is not involved in the accident. We noticed that the dataset was highly imbalanced as categories involving stationary vehicles, pedestrians, and obstacles made up less than 5% of the dataset, hindering the model training process. So we decided to fix the data imbalance problem by proceeding with the classes that have significant number of videos available in the dataset, as shown in the table here.
With respect to the knowledge graph component for this project, we utilize the metadata that is present with respect to the DOTA dataset in order to first design an ontology and also produce a knowledge graph that can be used for further context. So we, based on the annotations in the data set that we had, we decided on the ontology and also the relevant classes, relationships, and the properties that could be used. And also adhering to the properties of a knowledge graph, we decided it was reproducible, traceable, and extensible. And we use the metadata for all of the videos in order to populate this knowledge graph. In order to leverage this knowledge graph, in order to provide context, verbalization is a tool or instrument that we used in order to provide additional context in order to help for the task at hand. So in this case, since we had to predict the kind of class the accident was involved in, we use the information that is provided in the annotations and verbalize them into natural language and use them in order to train the models. So here is a simple example of a knowledge graph where we have nodes and the relationship between the nodes. And these can be converted into triples that specify the object, relation, and the subject. And based on certain templates that we can use, we verbalize these. And we'll delve further into the verbalization that we did for the task at hand. But this provides a general pipeline that we use in order to verbalize a knowledge graph. So some of the frame level verbalization that we tried out initially were first, whether directly using the triples, that is the subject, relation, and object directly as an input to the model instead of converting into a natural language. Would this provide any kind of contextual knowledge to the model? So that was for that was why we used the triples directly. And with respect to simple verbalization, we just mentioned a single sentence per frame that mentions the object in the frame and the kind of accident the object is involved in. And with respect to complex verbalization, we also use the severity of the accident and try to estimate the direction in which the object was moving in order to provide further context. And this also integrates a temporal knowledge since it tracks the motion of the object and also the severity of the accident across the frames. So this has multiple sentences per frame and was this was a complex verbalization that we used. So coming here, the simple verbalization contains of a single sentence, whereas complex verbalization, we take into account the severity of the accident, the direction in which the vehicle is moving in, and also the kind of vehicles that are involved in the accident. So this provides a much more extensive view of the accident. Additionally, we tried out few other video level verbalization techniques like the trajectory, acceleration, alteration, and the kind of collision. So here trajectory defines in which direction the vehicle is moving in, and also based on the bounding box information that we had, we tried to use the acceleration as to whether the vehicle was slowing down, was speeding up. So these kind of acceleration information was also verbalized, and also the change of shape of the object. Suppose after an accident, if there was any alteration in the vehicle shape, these were also verbalized, and also a collision between various vehicles. And in order to try out different combinations of these verbalizations, we combined various forms of these verbalizations, such as acceleration, collision, alteration, collision, and acceleration and alteration. So these were some of the other extensive verbalization that were tried out. Finally, since we also had to try out a simple class level verbalization, we took the class label and created simple sentences out of them in order to pass them as the simplest form of verbalization, which was fixed for each class and does not take in any other information. So based on whether, for example, other lateral would be a vehicle hits the sides of another vehicle. So these were fixed sentences that map the class to a specific sentence. So this covers all the verbalization that we did, and we will delve into the models in further section.
So moving on, let's look at some of the models that we explored in the process of building the end-to-end pipeline. We tried out two specific set of models. One was CLIP, which was for frame level classification, and the other one was XCLIP for video level classification. We tried out both binary and multi-class classification, where binary is to classify if the video is an accident or not, and multi-class was to give the video a definite class. And we also tried ego versus other classification based on the entity that is involved in the accident. So let's look at the first model, which was CLIP. CLIP stands for Contrastive Language Image Pre-training. It uses contrastive learning approach to predict whether the given pairs of image and text are similar or not. So contrastive learning in general is an approach where a model learns by contrasting similar examples while distinguishing them from dissimilar ones. So this enhances the capability of the model to identify the relationship between the data points. What we observed was that CLIP is able to understand the relationship between the images and the text rightly, and it enables zero-shot image classification. We finalized this model based on our experiments in the spring semester because it showed promising results compared to other state-of-the-art models such as Violet and Wilbert. So in our given pipeline, what we do is that we take an image, text caption, and a set of labels, and we produce a confidence score. And whichever class has the highest confidence score, that is considered to be the final class of the classification. So as I mentioned earlier, we observed that CLIP is able to understand the relationship between the image and the text, and it can be used in both zero-shot and fine-tuned ways. And we tried out a bunch of experiments with CLIP with respect to the class labels, such as we tried out generic and specific class labels, where generic meant car accident, truck accident, etc., and specific were the labels that were present in the data set. And with respect to different verbalizations, which was mentioned earlier, we tried out a bunch of set of combinations with CLIP. We tried out distractor captions, negative pairs, where we feed in the negation of the existing class or semantically uncorrelated labels or gibberish labels. And we also tried out a few experiments with images where we fed in only the anomaly frames, or we fed in both anomaly and non-anomalous frames so that the model understands how to differentiate between the two. But despite all our efforts, none of this really gave us any promising results. And these are the few issues that we identified with CLIP. So it had a poor zero-shot performance. That is, it mostly predicted majority class as the output. And upon fine-tuning, what we observed was that each class was predicted with equal confidence. I think around 10 to 15% confidence was there throughout, and we couldn't identify one class as the final classification. And it was unable to differentiate between the frames of different classes. That is, most of the image and text embeddings were very similar to each other, so it wasn't able to differentiate between the classes. And we weren't able to incorporate any other loss function during our fine tuning, and that did not give us good results as well. But the main part of all of this was that it classified each frame separately, and it did not involve any temporal context, which was a major issue, and we thought that needs to be addressed, and that is why we looked at another model called XClip.
All right, so I'll introduce XClip, which is what we use for our video level classification. So it's pretty similar to CLIP, except that it takes video as input, and it was actually initially developed for video recognition. But what's the important thing to note is that it incorporates temporal information through the video encoder, which has a cross-frame communication transformer. And on a high level, we're going to use XClip in two different ways. The first is just using its video encoder to get the video embeddings and then passing that through a classification head. The second way is to use the entire architecture, in which we will use the text encoder by passing in our verbalizations from our knowledge graph. So in order to test the capabilities of XClip, we first did the most simple approach of just classifying whether an accident exists or not. So that's the binary classification. And here the input is going to be the frames that are before the anomaly time span will be the negative label, and then within the time span will be have a positive label. And we're going to use just the video encoder for this architecture. And with this, we got reasonable results with about above 0.7 for accuracy, precision, and recall. And moving on to the more complicated example of multi-class classification, here's a pretty similar architecture, except the input is just going to be the frames within the anomaly time span, and the label is the actual anomaly class. And we see an accuracy of 0.35, so there's definitely room for improvement. When looking at the class level performance, we see that the other classes, the non-ego classes, do perform worse. So we do hypothesize that the ego versus non-ego videos are too different for the model to capture, since the viewpoints are quite different in where the accident occurs. So we think that's why the model's having a hard time classifying them. And that's why this motivates us to have separate models for ego and non-ego.
So based on the ideas described earlier, this is the final end-to-end pipeline that we decided to give a try. So given an accident video, we first pass it to the initial model, which identifies whether it takes place in an ego setting or a non-ego setting. So after this classification, the video is then passed to the respective model for ego and non-ego classes, and we then obtain our final classification. So we'll now go through each of these models in further detail. So this is the first model that identifies whether it takes place in an ego setting or a non-ego setting. And as stated earlier, our earlier experiments with one single model for identification of this did not work. So we decided to separate the two. And the main reason for this is that when we use a classifier head, it tends to learn the characteristics of egocentric and non-egocentric settings separately. So the way we did this was, given an anomaly video, we pick out 8 anomaly frames that are uniformly distributed from the time range. So we get this from the annotations of the data set. We then pass this into the XClip model to obtain the video embeddings that Amanda stated earlier. And then we use linear layers, so 3 linear layers with ReLU activation. And that's how we obtain the classification of whether it's ego or non-ego. So the accuracy we saw for this model was 72.53%. So once we obtain the classification for this, we direct it into the respective model. So for the ego setting, it is very similar to the previous one, where we use the XClip video embeddings and 8 frames taken from the anomaly time range. So here we did experiment with four main classes, which is ego moving ahead or waiting, ego oncoming, ego turning, and ego lateral. So this is based on the data we obtained after balancing our data set. So we did experiment with different classifier architectures, but in this case, we didn't really see much improvement with changing the linear layers. So we finally stuck to 4 linear layers with ReLU activation, and we saw an accuracy of 64.16%. And then for the non-egocentric setting, very similar, but here we stuck to 3 main classes, which is other moving ahead or waiting, other turning, and other lateral. So here we did see a little bit of change with the classifier architecture, and the best performance we saw was with 4 linear layers and ReLU activation. And here the accuracy is slightly lower because in the non-egocentric setting, it is difficult for the model to differentiate between the accidents. So we saw an accuracy of 56.23%.
Because we see the discrepancy between the prediction on ego and others, so we think we should try another architecture to see if we can provide the model with more text information. That's why we tried the fine-tuning XClip with text on only the other categories. So the idea is really to align the video frames and text in the same embedding space using the data that we have from the DOTA dataset. So the architecture works as follows. For the input, we'll still take in the video frames, but we will also construct the verbalization and put that as text input into the model. So how we construct it is that we'll use both the class and video level verbalization. So for example, if we have 3 classes and then the middle class is actually ground truth class, then we'll first put in all the class level verbalization. And then for the ground truth class, we'll also add in the video level verbalization, in this case is the trajectory information. And then we tried different combinations. The best results we get is 46.9%. And actually a bunch of experiments that we tried is listed on the right. So just the reason behind why we tried these different combinations of the verbalization is that for clip and XClip, it both has pre-trained like context length limit of 77 tokens. So there is a limit on how much information we can actually put into the model in terms of text. So that's why we try different combinations to see which can give us the best results. So we think across all of the experiments, the best we can find is the alteration plus collision. So basically the shape information and if there's like collision. And that give us recall precision accuracy above 40%. And across the table, we can see that for some of the combinations, it still has a high accuracy, but low recall and precision. And then upon further look into that, we actually saw that is because for some of the labels, it is predicting the majority class. That's why the recall and precision is lower. And then based on this result, we see that the accuracy is not higher than the previous model that we tried on the other. And then just based on all the knowledge that we tried from CLIP, from XClip, we finalized this end-to-end pipeline to be the 3 model architecture. So basically the input will be the frames from the videos across anomaly time range. And then as the first step, we'll put that input into the egocentric versus other classification. And then it will give us the results on whether this video is taken from an egocentric view or whether it itself is not involved in the accident. And then as a second step, then we'll take this prediction and then pass that into either the ego or non-ego model to give us the final prediction. And then across the pipeline, this is 48% is the final accuracy we got. So this is the results that summarized across the different experiments we did, and these are the numbers we got. So for the first 2, those are from CLIP. We can see it's actually slightly lower than the XClip that we tried before. So that makes sense because for the XClip, it does take in the temporal information, which is across frame attention, and then that potentially give us more information across the temporal time. And then for the XClip, we see that when we are trying the accident versus non-accident, it gives us above 70% of accuracy. And then when we try the final combination, which is these 3 models, it gives us a lower accuracy. We think this is because like for the task itself, when we are classifying whether there is an accident, it is easier than if we are predicting what class of accident that is, the accident actually is. And then finally, this is basically all the results that we get. We did try different models, but we at the end, when we choose the end-to-end pipeline, these are the knowledge that we primarily used.
So just looking a little more into the details for what's going into our model. So for clip, we had single frames. For XClip, we had videos, but these are the frames from those videos. So here we have what our model predicted versus what the actual tag was. So for clip, this is actually being assigned to a single frame rather than XClip. This would be like a set of frames in a video. Here we see the actual label is ego moving ahead or waiting. So ego means that this is a dash cam and the car that has this dash cam is actually involved in the accident. And the moving ahead or waiting is just the type of accident. So we predicted oncoming as the label here. And as we can see, it's actually not super clear, what like the difference is necessarily between these types of labels. They're often very similar. So that contributed somewhat to some errors that we have in our model's outputs. And here,
so the actual is that I'm about to hit something, and
yeah,
the predicted is something is about to hit me.
Exactly. So it'd be coming towards you instead of you going towards it. So you still have that motion. And here we see this is the correct example where there's a lateral movement. So ego, again, the car is involved in the accident, but it's coming in from the side. So these are just two typical examples, both ego, meaning the car is involved. So a brief error analysis for the models we experimented with the most. So clip, we saw often acted as a majority classifier for most situations. So this was when essentially we're looking at a single frame. So it's just often when we go throughout the frames, it's just taking the majority class, which obviously is not what we want. And as mentioned earlier, frames of different classes are not necessarily distinct. So if you're looking at frames at 20 FPS, which was the typical frame rates, we're seeing not much disparity between frames as we go along, and it's hard to classify them individually. And then for XClip, we also noticed that our model experienced a lot of overfitting. So even though we actually had decent accuracy for the models that we were able to choose that had a high validation accuracy, eventually they tended to reach 100% on the training accuracy. This suggests we might need some more data, which we had issues with throughout this project. So moving on to some limitations with our project. So we also had in addition to having not so much data, we had a pretty unbalanced data set. There were we had ultimately 20 classes of data and then 20 labels, and we sort of grouped them together and had to use different techniques to balance this data set, which gave us even fewer classes to work with. Some we had to discard for the purpose of this project, such as the pedestrian class, which there are very few examples for. Also, the videos themselves are very short, and sometimes the anomaly within the video is even shorter. So you're talking less than a second sometimes of just the accident taking place, as well as the context length that we're feeding into these models was very short. So the complex verbalizations that you saw earlier, we have to keep them within 77 tokens, which causes some limitations for what we could experiment with. The videos themselves are relatively low quality, and there's also different viewpoints that may be obstructing the camera angles. There's precipitation, there's darkness that could cause issues with how the model perceives things. And we also see that there are, so as mentioned earlier, just the frames differentiating could be a struggle, and the class labels themselves. So you have classes that are, as mentioned, very similar with a vehicle oncoming versus you heading towards a vehicle, for example. And finally, the cameras themselves are often moving. So if you're in a vehicle, the car is moving, and this causes an additional area of complexity. So in addition to just being ego versus other, you also have that motion that's involved. So for future work, we wanted to, there are a few points that we didn't really get to that we were hoping to, and that could be gone with further. So this user interface, we have like a very brief example here of what it could look like, but basically we think that this could be more of a tool that could be used by people that are monitoring traffic themselves. They could look at a video and see what the output could be as a predicted label. We also hope to be able to leverage language models more in the future. We think that experimenting more with some complex verbalization techniques could be useful. And we also think that having more data, not just in terms of videos, but modalities could be useful. So we didn't have any audio in this instance, but we think that could provide some useful information. And finally, the data itself, we would like to have more data sources and hope for more generalizability. So not just egocentric data from a car, maybe from different viewpoints could be useful as well. So that's the summary of the future work. And that's all for now. So thank you very much.
So I think that one question that came up for me fairly early is whether you're constrained in any way by the ontology that you picked. So do you think that you know, there were gaps in the ontology, and then also whether you were limited in your ability to fit the videos to the ontology to create the knowledge graph. So if you go back to the one picture with the cars stopped on the highway. So I think what's interesting about that one,
Later?
Yeah.
This one?
Yeah, so I mean, when I look at that one, the most important thing is that I'm you know, moving ahead, I'm waiting, and the guy in front of me doesn't have his backup lights on. Okay, so if anything's going on here, I'm hitting that guy. He's not coming with me, right? So to me, it's easy to figure out that it's not ego oncoming, because if he was coming at me in this context, I'd have to see the front of his car, or I'd have to see his backup lights. So that leads me to believe that, you know, it might be, you know, a situation where to discern some of these cases, especially with a smaller number of data elements, you'd have to actually have a richer representation than just the verbalizations that you get, you know, from the metadata and knowledge graph. It's a great place to start. But I bet if you plug this image into your human interface, they would basically say, oh, cars stopped on the highway, doesn't look like an accident.
Right, yeah.
Or, ooh, cars stopped on the highway, but the backup lights are on, better watch out, better keep your horn. So I think, you know, an appeal to sort of human intuition about what kinds of representations would be helpful, you know, might be interesting. I know you were focusing more on augmenting with text, but when I think about this, I'm also thinking about ways of augmenting the computer vision side.
Yeah.
So humans can tell whether or not an accident has happened from a single frame. And basically, if there's deformation or it's clear that the, you know, bounding box, you know, of the two vehicles is overlapping, there's no way, you know, that can happen, you know, without an accident being present. If they're really close to one another but not touching, then I might need to see if they were, you know, moving at a slow rate of speed and then, you know, turning away from one in the future. So it's a little more subtle. But if I'm watching that out with my dash cam, I'd say, oh, no, because I'd be expecting something to happen. So this leads to another question that I had, which is, do you feel that you were limited at all by the fixed window size of the 8 frames before and after? Or is it really that's all you could do because the videos were super short?
So good question. And just to comment before on what you were saying about, like, for example, bounding boxes, we did actually experiment to some degree on, like, even what you're saying exactly, like seeing where bounding boxes are relative to each other, if they're close to each other. And what we found was, you know, often like there was a variety of different cases where this happened. And like sometimes you have things in the distance, sometimes you have cars that are close, sometimes you have pedestrians with different bounding boxes. So what we noticed was there was never really like a set rule. So even if you saw like two bounding boxes right next to each other, it could be that one is very far and one is very close. For example, that wasn't actually an accident, but that was definitely something that we could definitely leverage more. In terms of the frame window, we did also experiment with different lengths. So we did, for example, 8 frames and 16 frames. As you mentioned, some of the videos are just too short. We had to discard some if we chose 16 frames. And like we sort of were deciding if it was worth the trade-off to actually just get rid of more videos and have like fewer overall with 16 frames, or, you know, have a smaller window and have more videos to work with. We ultimately went for the 8 frames. We did notice there were actually minor improvements in accuracy when we did 16 frames, but there were a bit inconsistent results. We didn't have like super high precision or recall there. But we do think that like it sort of suggests that if we had more of a window, more temporality in there, it actually could make a difference for sure.
Okay. So you guys did a great job evolving your architecture as you learned more about the problem and more about the data set. And that's super. I think that's really a positive outcome for your project, because that's what professional data scientists do. Okay, so they're sort of upholding the brands, of MCDS. But let's say that I was now going to put you in charge of this project at a company. Maybe I have my own startup that's going to be competing with Bosch, hiring you all the way, to sort of really make this happen. And I'm going to give you, unlimited budget. Okay, you can do whatever you want. What do you think is the right thing to do? My hint here, of course, is probably data curation and collection is the most important thing. But let me know what you think right now. If we had unlimited budget to push this ahead, what should we do?
So like you said, I think our first priority would be to get more data. Right now, we have lesser number of videos, really unclear videos, and a highly imbalanced data set. So we want to either work with DOTA itself and try to get all of the data available and make sure that it's balanced, or try to so we did explore other data sets in our Capstone, but I'm sure there's much more out there that that's out of our computational reach currently. So maybe we would try to leverage that, or just build our own data set, even though that's the harder way to go, because in the end, what we want is high quality videos with clear distinctions between accidents, just so that the model is able to learn it.
I see.
Yeah.
So maybe because Bosch is an OEM and they're not a car manufacturer, they don't have direct access to actual data that might be generated in cars. So we might want to go to Honda, want to use Professor Saker's connections with Honda and say, hey guys, can you start sharing camera images and, data from your OnStar system so that we could build a massive data set of egocentric videos. Okay, that's an interesting.
I think our initial mindset was to actually not even have cameras in cars. It was actually stationary cameras on the street. But that's an even more difficult problem.
See where I'm going with
Yeah.
this. Okay? So if manufacturers are already moving towards the idea of having a dash cam,
Right.
and they're also moving towards the idea of providing services. Okay, so what's the next? And we all know that cars can do collision detection. So what's the next generation there? Well, it's a camera that can look downrange and tell you to pay attention, because it looks like, hey, there's a guy stopped, at the exit there. He might try to remerge from the slow speed.
Yeah.
Or wow, there's a person overtaking on the right, at a high level of speed, which right now does not generate any alert at all, unless I, turn on my turn signal and try to move there. But I definitely would want to know about that. I was thinking about it. So I guess graduating from being an academic data scientist to being more of an entrepreneur would be to think about sort of where in the world are we going to be able to get this fairly soon. I do like the idea of instrumenting the static cameras. I think there are probably high accident zones that need to be studied, and where the cost of putting in full instrumentation is probably worth it, right? So I think in Pittsburgh, it's the corner of 18th Street and Carson Street in the south side, which is only a couple of blocks from my house, which is the place that has the most accidents, pedestrian accidents, you name it, because it's a place that has the most drunken pedestrians and the most drunken drivers, at certain times of the week. So that might be an interesting.
Yeah, that was actually something else that we observed in our experiment, that classes with pedestrians or obstacles were less detected than just accidents between cars and trucks, etc. I think this is because the model was unable to differentiate between the actual person there versus a stationary object. It was getting confused between what it was. I think that's because of the low quality of the videos. Like you said, if we had stationary cameras that were focused on just intersections and providing high quality videos to us, maybe the model can differentiate between tinier objects better.
Well, and it's also we can't really expect Clip to do very fine-grained object detection and have such small data to learn from. I was peering at that one of the pedestrians to see whether there was a helmet on, because I was wondering whether it was a cyclist. Okay. And you would not be able to tell whether the backup lights are on unless you do more like object detection as well.
And
So it's okay to sort of propose that in the future, we not only need the data, but maybe, you know, more sophisticated models so that we can understand what's going on there.
Yep.
That's what was behind my digging a little bit on the ontology and knowledge graph. Because if you look at what's done today in visual QA with the kind of scene graphs that teams are trying to produce on even a single 2D image, they're a lot more complicated and sort of decompose the image into finer grained objects and relationships between them. That might be very useful. Mentors, do you have any questions?
Well, their comment, we sold the camera business fortunately, so if you want to go to home, I go to home. I know that, you know, so first of all, great presentation. I mean, that was a very complex project where all the limitations actually, I think equally the problems you find in the real world, so you don't find always very nicely annotated data, the data are unbalanced, and so on and so forth. With respect to the ontology, maybe you know what the student mentioned at the beginning. So we provided an ontology that we developed at Bosch to describe scenes in general, and we aligned that with the schema of the metadata for the dataset. So definitely is a good point that some of the constraints and axioms that are in the ontology might not have been at the right level of representation that could have been used for improving some of the relations in the objects annotated in the data. And other than that, it's also interesting to see in the verbalization experiments where we had to deal with the limitations from the token size. So I think there are interesting results from the combinations of the different verbalization, and it's quite exciting to think about if you have a language model on top that uses all the verbalizations as an input and tries to summarize the scene within that time constraint, the token constraint. That is something we can even look in the future, and I think there is material also for publication. So we see if we're able to
what impressed me about this was that if you had the most important or most likely one sentence summary of what's going on in the image, that's obviously going to be much more succinct than the full verbalization of the data you have in the knowledge graph. But it's probably going to be the most salient thing for deciding whether it's a match. So, cars, I'm waiting with cars in front of me to get onto the highway. Okay, that's a fake situation. So the majority vote there is not going to be, necessarily. So, and, everything I'm saying about having more detailed scene graph works against the fact that if you verbalize everything you have in the scene graph, then you end up with this giant, paragraph that's, going to be hard, to inject into a model. Maybe you can use that as a prompt, on a GPT style model.
Right. I think it goes hand in hand to some extent because perhaps you verbalize everything in scene graph, at least you expect to have coverage over the ontological aspects in the context. And I've seen several works these days of actually taking that context, optimized it from a learning objective to actually fit it to be more salient for this particular task. That could be sort of decoupled from the actual downstream learning objectives for classification itself.
Yeah, the thing with scene graphs that's super hard is generating the scene graph is really context sensitive. So the students in the DQA project have this stock image from the DQA data set, which is a man and a woman who are sitting at a wooden picnic table, and then there's a big bridge behind them. And then, the question is what should be in the scene graph here? Suppose I'm a civil engineering student who's studying bridges that are made with a stone footing. Okay, and they ignore the people in the foreground and focus on the structure of the quality of the bridge. actually context dependent. So I think maybe there's an interesting future hypothesis for you guys, which is, okay, here's a start, but what is an optimal ontology or KG for doing this kind of thing? And maybe rather than just being restricted by the metadata that you have with the DOTA data set, you would just go with the images and then have humans talk to you about what they thought was important, for deciding whether or not, an accident was happening. And then you very quickly find, cars that stand still, backup lights on or off, facing me, not facing me, would be the things that humans, would be thinking about.